Hi everybody, my name is Overtime and I want to tell you about our work on plug-and-play task level autonomy for robotics. This work was performed by myself, my colleague Dan Squeezer, under the supervision of our advisor Professor Brafman. Our agenda today will talk about the motivation regarding robotics and AI planning, existing systems, gaps we found, our solution, an experiment video, and an illustrative example. So first of all, some background. Why do we need autonomous robots? So first of all, why robots? Because they can work in dangerous environments, perform dangerous tasks, some repetitive tasks that we don't want humans to do. They have different physical features, like they can maybe lift heavy liftings or navigate inside the blast stream, things that a human can do. Why do we want them to be autonomous? Because we don't want always people to control them. So let's look at the history. This is shaky. It's the first AI operated robot. It was developed in the 60s, late 60s, early 70s. It has a set of basic skills like navigating, turning lights on, and things like that. And its AI engine, which scheduled these skills, it was called Strips. Now, Strips, it's also the name of the AI planner or AI solver. That is the algorithm that is actually deciding which skill to schedule. And Strips is also the name of the formal language you describe the planning problem, like the different objects in the space, the state itself, what you want the robot to achieve. So Strips, it's also the name of the planner, and I want you to remember these three concepts, which is basic skills, an AI planner, and a formal language. So let's do a short recap about AI planning and POM-DPs. So in AI planning, we want to solve a planning problem. This planning problem, we have a state of the world, the current state of the world, and we want to reach a certain state, and we can change the state of the world using some actions, and our agent needs to select the best actions. Now, there are different models to describe planning problems. Some of them are deterministic, which means that every action deterministically changes the world, and the one that I want to talk about, POM-DP, it's probabilistic, which means every action can change, traverse the state of the world from one state to another in an undeterministic way. So I have a distribution of possible states when I'm activating an action from a certain state. Also in POM-DP, I don't know my current state. I don't know the state of the world. I only maintain a belief state over the state of the world. And after I perform an action, then I received from the environment an observation which helps me to update my belief on the world. I also receive a reward, and my goal is to maximize the rewards given to me from the environment over time. So if I want an AI solver to solve my planning problem, I need to describe my planning problem and to give it to it as an input. So I have two ways to describe my planning problem. The first one is an exhaustive description. This is good only for tiny problems. For example, if I have a problem in my world that I have 10 Boolean variables, then my state space will already be around 1000 possible states. And if I want to describe my transition function, then I need a table of around 1 million cells. So for normal interesting problems, then it's not enough. So this exhaustive description, it's not something which is practical for interesting problems. Another way to do it, which is usually how it's done, is to describe the problem using action description languages. In this example, we see RDDL, which is quite an expressive ADL, and it describes here the wildfire domain. And what we see here, without getting inside the details, in here we have a grid cell of 9 cells, and each cell, it can have fuel or not have fuel, and it can be burning or not, and it can be a target or not, and the agent needs to put out the fire so it won't burn the target cells. So it has the action of put out, and in here we can see that it has state variables of burning for each XY cell, and it describes after a set of states that a cell which has fuel, it can be randomly, it can start to burn randomly, and we sample if it's burning or not using this Bernoulli, from this Bernoulli distribution using this variable. So in here we can compactly describe a transition function because we have a large, the state space here is pretty big, but we can describe it in a compact way. We have a claim. We say that current ADLs, they are not enough. Why they are not enough? So mainly because they are not expressive enough, and also, which is less significant, that it has a larger learning curve for software engineers because it uses slightly different concepts. So let's talk about why they are not expressive enough. For example, if I want to describe that one of the cells it starts to burn randomly depending on whether it has fuel, just one cell, it's very hard to do it using RDDL. In here they are describing the probability for any cell, but if I want to make a condition between the different cells, then it's something it's hard to describe. It's only if you're using if else. So this is okay when you have 9 cells, it will be big, but you can do it. But if it's more than that, it's very hard, so it's not expressive. While loops will solve it easily, but they don't have while loops. And the other thing is, what if I want to describe in here in this Bernoulli, I want the parameter here to be something a little bit more complex than what they are describing here. Let's say the second derivative of a function or something more complex. So in RDDL it will be hard or impossible to describe it. And what we think is needed is an ADL with the power of a general purpose programming language. More specifically, we are talking about C++. C++ is also widely used in robotics, so the engineers, they know this language, and C++ has a large set of implemented code to construct and manipulate data structures, and both of these, the example I gave, they can be easily solved using C++ and a lot more. It's easy to describe the complexity of real-world problems, type of problems we want to model when we have robotic domains that are complicated. Okay, so we saw what happened in the past with Shaky, but what's going on today when we are developing autonomous robots. So we talked with engineers from two major companies working on autonomous robots in Israel, and we saw that the way they are doing it is very similar in a way to how it's done for Shaky. First of all, you have the robot skills. The robot skills today we have more advanced robot skills, but we have robot skills like identifying objects or manipulating them with arms and things like that. So we have the basic robot skills. Then we have a mechanism to schedule these skills. Usually what they are doing today, they are using handwritten scripts, not using AI planning or something like that. We saw that these handwritten scripts, it's very hard to write them. Why? Because unlike virtual software, when you're doing 1 + 1 = 2, everything is deterministic. In the real world, things are not deterministic, and it's very hard to write a script, to write a policy for such agents. And also, you have partial information about the world. You don't know the real state of the world because you only sense some aspects of the world, and also the sensor, they can be noisy, so it's very hard to write a script. And also, after you did all this work on writing a script, think that the environment, it can just change, and then you need to write everything again. So then they need to write everything again, and so it's very hard to write it manually, so they have this difficulty. And why don't they use AI planning? Then you can just describe your problem, you can just change your problem, and then it will be solved automatically. So the thing is that there is a significant integration effort to work with AI planning, and also there is a gap between robots. They work on they have continuous variables and everything is very low level, and when you're describing a model for AI planning, then it's something more abstract, only things that are important for decision making. So there is this gap also. There are available systems to integrate AI planning with robotics. There is ROSplan that support PDDL. It's a type of deterministic planning with numeric resources, and they also support RDDL in a limited way without partial observability. They require significant integration effort. We experiment with their system, so it's not straightforward. There is also the CLIPS Executive, which has a goal reasoning, high-level predefined plan, and each of these goals, once they are decided they want to pursue a certain goal, then they have a PDDL planner that solve a problem to achieve this goal, and by the results of this plan, then they know how to traverse in this goal tree and to pursue the next needed goal. And also there is a skill-based architecture introduced by Alexander Albor and friends, which propose a formal language to specify robot skills like their own ADL, and they also have code auto generation to assist the user, yet the user still need to write some code, and also they use PDDL as a planning as a model, which means that they don't have probabilistic actions, not even to say noisy sensing. So this is limited to replanning if something happens which is not expected and can cause a repetitive behavior from the robot. So the gaps we found is that the current ADLs are not expressive enough for real-world robotic problems. The available systems, they require to write code that stitches the robot skills to the system, so there is a significant integration effort. Some of the systems, they are tightly bound to a specific robotic framework like ROSplan, and we want something general because today it's ROS, tomorrow it's IoT or something, so we don't want to be tightly bound to any system. And also these systems, they don't support noisy sensing, which is a key characteristic in robotic domains. So our solution, we introduced the autonomous robot operating system, which is a complete set of methodology and tools to bridge the gap between robotic skills and AI planning. Our users will give the implementation of the skills, and now each of these skills will be documenting using our generative skill documentation language. This is our ADL, and there will be an environment file to document the possible state variables and the robot objectives, and an expressive abstract mapping will document the bridge between the robot code and the abstract JSDL, which is more abstract than the robot code and the public variables and things like that. The AOS will be a plug-and-play solution, which means user will only give their documented code, and the system will do all the generation of the code that needed to stitch between the skills, and everything will be performed automatically. So let's look at our architecture very shortly. What we expose is a web API. The users can send HTTP requests to integrate their code, and also after the system is running, then they can query about the inner state of the system and perform other actions to control the robot, like shutting it down. And also, once a user requests to integrate his documented code, then we add the code to the planning engine based on the model described in his documentation. The planning engine decides which skill to activate, and we have the unifying layer for communication between the different components. And also we auto-generate the functional layer middleware. This component tells the robot itself, which is the functional layer, tell the robot which skill to activate, and also it listens to the traffic inside the robot framework, and based on that it returns a response, which is the observation from after executing the action, and then the planning engine can reason about it. Let's see some experiments. Okay, so in here we are using our Panda robot. It's a robotic arm. In this experiment, we just wanted to see how easy it is to connect the robot to the system. It has two deterministic skills. One, it can draw circles in each one of the grid tic-tac-toe cells, and the other one, it can observe when the grid cell state changes. And what we did, we just documented it, and we documented that it receives a special reward when it reaches certain states, and a penalty if it loses. And we saw that it's acting in a sensible way. This is what we see in this experiment. But as I said, in the planning problem itself, it's easy to describe. In the second experiments, we see the armadillo. In here, what you're seeing here, I'm just running the server of the AOS, and you will constantly see that I'm running a HTTP request. These are just to query what is the inner state, what the robot believes the state is. What we had in this experiment, we have a few skills. One of them is a pick action, which we did it so it's not perfect. Sometimes the robot can drop the can, and sometimes after it's dropping or succeeding to pick up, it doesn't know the real state. So it has also noisy observation, and we document all of this using the ADL, and we saw that we are receiving good behavior, and also we can document it. So these are our experiment. Now let's see an illustrative example of the system, of a documentation given to the system. In this example, in this toy example, which is a toy example but it's also very rich, we have a robot with a single skill. It can also navigate, and the mission of this robot is to navigate as fast as possible between 3 known locations. The robot's initial location is unknown. It starts in the first location with a probability of 50% or 0.5. If it's not there, then it has it's 80% in the third location. Otherwise, it's in the second location. So we don't know the initial state. And also, this robot, if it starts navigating when it doesn't know its location, or if it loses its location during navigation, then the skill takes a lot more time. Okay, and it's important for us because we want to do it as fast as possible. And also the navigation skill has a 10% chance of failing, causing the robot to lose its orientation. And if you are telling the robot to navigate to its current location, then it loses its orientation. And the robot mistakenly reports success in 20% of the cases that the navigation action fails. So of course, when you're working with our system, first of all, you need to experiment with your skills. You need to know how they work, and then you can document it. And this is what we did here. And also, we prefer that we have a preference that the robot will not visit the first location before it visits the second location. So we have a preference, but our main goal is to reach all of these locations. And there is also a 5% chance that a person occasionally moves the robot and causing it to lose its orientation. So this is an extrinsic event, something that the robot it didn't cause the change in the environment, but there is an extrinsic change in the environments regardless of the robot decisions on which action to take. In our documentation, you have 3 sets of variables. You describe your state variables, but we store them in 3 replicates. One is to describe your previous state when you want to describe how your state changes when you want to document your skill. So one set of variables to describe your previous state, another one with one underline to describe the state after extrinsic changes, like when on occasion a person moves the robot or something like that. And the third one is to describe the next state. So first of all, you need to describe your environment file. You have a list of variables you can define. You can also define the initial belief state. Everything here is in C++, the description. This is a JSON file. What you see here in strong blue, these are saved word. Okay, we have a schema, JSON schema, and this is the description. You can describe special states which are desirable or undesirable. Like in here, you can see you have a preference not to visit the second location before you visit the first one, and then you will receive a one-time penalty. And you can describe your goal, and then you will receive a significant reward, and the robot also will stop because this. And we see here the extrinsic changes dynamic model also. This is the JSDL describing the navigation skill. You can define the precondition, like I don't want to tell the robot to navigate to its own location. I'm giving here a very general overview just for you to see, and I can also describe the dynamic model, what happened when I activate the system. So the discrete location of the robot, then it will be if I'm not meeting my precondition, or I have a 10% chance of failing, then I will lose my orientation. Otherwise, I will reach the desired location. This is a parameter given to the skill. Okay, so this is a parameter given to the skill, the location I want to go to, and this is how I'll get it. I can also describe here my responses, and in here I'm describing a noisy response. I'm sampling from a Bernoulli distribution, and I can also describe here the rewards given, the cost of the action, and possible rewards that this action can give me. And in here I'm describing the abstraction mapping. So first of all, I'm describing local variables. These local variables, they are a function of public variables of the robot framework, and we are summing them into these variables. So in here we can see we are listening to a ROS topic, ROS out. This is simply the logs of the robot, the logs of ROS. And we are saying in here, we can describe here in Python, and we are saying that if we have a goal reached send inside the log, then we know then this variable called goal reached will receive a true value, and we are starting with a false value. So in here the programmer can very flexibly describe things going on in his environment with all the flexibility of a programming language, Python in this case. So also it describes other local variables, and then it can describe what is the actual observation. What is the actual observation sent to the robot after I'm activating the real robot? Then what is the observation received? So I will receive an observation of success if this is a condition on the local variables. Otherwise I will receive fail. So I can describe my observations, what will actually happen when I'm activating the skill, and also I'm describing how I'm activating these skills, so the AOS can activate it automatically. In here I'm describing how to activate a ROS service. So that's it. Thank you.